Welcome to Keentel Engineering. EMT models in PSCAD/EMTDC have become the currency of modern interconnection. Grid operators, transmission owners, and study engineers increasingly require them as formal deliverables, not just for study purposes, but as part of the interconnection submission process. That shift created two practical problems with very little to do with model physics and everything to do with how the model gets handled once it leaves the team that built it. In this video, we walk through both problems and their solutions: the black box feature for sharing a model without exposing proprietary control logic, and the independent C-code feature for taking validated control logic out of the simulator entirely. Both are covered in PSCAD version 5.1.0. The two problems are distinct and they require different solutions. Problem 1. You need to share a PSCAD model with a grid operator, a study consultant, or a third-party reviewer, but the model contains proprietary control logic you cannot hand over. The black box feature solves this by collapsing an entire module hierarchy into a single compiled non-module component. The result preserves exact simulation behavior while sealing the internals. The recipient gets a working model. They do not get the source. Problem 2. You have validated control logic inside PSCAD that needs to run outside the simulator, on a hardware-in-the-loop test rig, an embedded controller, or a digital twin platform. The independent C-code feature solves this by translating a control module into portable standalone C-code that compiles and runs completely outside PSCAD, including on bare metal hardware. Same PSCAD release, two complementary tools, two different directions. One keeps the model inside PSCAD but hides it. The other takes it out entirely. The black box feature is not a cosmetic wrapper. It regenerates the model as compiled machine code and rebuilds the component around it from scratch. The algorithm works in 3 steps. First, Fortran source generation. The module is emitted as a Fortran file formatted to run with EMTDC as an external file, with a subroutine structure that supports multiple simultaneous instances. Second, object and library file creation. The Fortran source compiles into an object file, and any nested modules bind together into a single static library. This is where the real protection lives. The logic is in compiled binary, not source. Third, automatic component creation. A new component definition is built from the original hierarchy, carrying over every port, parameter, and graphic. The internals are sealed. The algorithm processes the hierarchy from the bottom up, innermost modules first, finishing with the top-level module last. A deeply nested control structure is fully absorbed into the compiled output with no intermediate layer left accessible. There are 2 restrictions that must be planned around before applying the black box feature, and both need to be resolved at the design stage, not after the hierarchy is built. Switches, sliders, dials, and radio links imply live, real-time user interaction. A compiled component cannot expose these the same way the original module did. Once sealed, those controls are gone from the interface. 2 options exist. Option A is to bake in a fixed value. Replace the dial or slider inside the module with a constant tag set to a preset value. This is clean and simple, but it permanently locks that parameter. There is no real-time variability left once the component is sealed. Option B is to preserve real-time control. Move the control or radio link out of the module entirely, promoting its signal upward through every intermediate hierarchy level using ports or parameters until it reaches the top level. The control then lives outside the sealed schematic and drives the component as an external input, retaining full live adjustability. The choice determines whether the sealed component is a fixed behavior artifact or a configurable one. Deciding this before building the hierarchy saves significant rework. New in version 5.1.0 is explicit handling of transmission line and cable models inside a black box. Line and cable models carry solved segment data that has to be stored somewhere, and a portion of that data remains visible to the recipient even after the module is sealed. Tower geometry and cable configuration stay hidden, but the nature of what remains visible depends on which line model was used. With the Bergeron model, the exposure is higher. Steady-state frequency, line length, phase count, and impedance and admittance data are all readable. The basic electrical character of the segment is accessible to anyone who examines the compiled output carefully. With the frequency-dependent phase model, the exposure is substantially lower. Only line length and phase count are directly visible. The remaining data consists of poles and residues from the curve fitting process, mathematically opaque to anyone who did not build the model. If concealing transmission segment design is a priority, the frequency-dependent phase model leaks far less usable information than Bergeron. Where the black box feature keeps a model inside PSCAD and hides it, the independent C-code feature does the opposite. It takes a control module out of PSCAD entirely. The output is portable, standalone C-code that compiles outside PSCAD and runs on any target platform, including bare metal hardware with no operating system. The use cases are hardware-in-the-loop test rigs, embedded controllers, and digital twin environments where the control behavior validated in simulation needs to execute in a real deployment context. Before generating, 3 type families must be configured to match the target platform. Integer types can be set to 16-bit short, 32-bit int, or 64-bit long. The PSCAD default is 32-bit. Floating point types can be 32-bit float, 64-bit double, or 128-bit long double. The default is 64-bit double. Complex number handling requires an explicit choice because compiler support varies widely. Options are no complex type, C99 standard complex, or a struct-based implementation for compilers such as MSVC that do not natively support complex types. Getting these type selections right for the target environment before generating avoids significant integration work on the receiving end. The independent C-code generator produces output in 3 folders. The libs folder contains PSCADlib.h and scadlib.c, the source for all C export-enabled PSCAD components. The headers folder contains auto-generated headers, 1 per module including submodules, named to match the definition source. The source folder contains the C implementation for each module, 1 file per module. The generated code is called through a run function that accepts a run type value. Run type 0 is a standard run. Execute the current time step normally. Run type 1 is last time step. Complete the step, then clear memory. Run type 2 is cleanup only. The last step already occurred, clear memory without running. Memory allocation defaults to static, which is required for hardware targets that forbid dynamic allocation. Switching to dynamic allocation enables multiple concurrent instances but must be reapplied after every regeneration. Not every PSCAD component can be translated by the C-code generator. 2 conditions must both be satisfied. The component must have no electrical aspect, and its mathematics must not be proprietary to PSCAD. Components that are supported include constant and time components, data type conversion components, and most CSMF, continuous system model function, components. These cover the vast majority of control logic built in PSCAD. Components that are not supported include the PID controller, the discrete wavelet transform, and the FFT and harmonic distortion calculator. These rely on mathematics that is internal to PSCAD and cannot be reproduced in Portable C. The quick way to check any component before committing: open its definition, navigate to the script section, drop down the current segment selector, and choose C. If a C script section appears, the component is C-coder ready. If it does not, it is not exportable. Both features appear regularly across 2 sides of interconnection-grade EMT work. On the study side, black-boxed EMT models are routinely received from equipment vendors and developers as part of interconnection submissions. Model quality review requires knowing precisely what an obfuscated model still reveals: line lengths, phase counts, the presence but not the values of passive branches, and what it has genuinely sealed. That knowledge shapes how an externally built model is validated and how residual exposure is communicated to a client preparing to hand off intellectual property. On the development side, the work runs the other direction, packaging a client's control design for distribution to ISOs, transmission owners, and study consultants without surrendering the logic that repro. Here are answers to 5 common questions about the black box and C-coder features. What does black box actually protect? It compiles your module hierarchy into machine code, so the source is unrecoverable. What remains visible depends on your settings. A reclosing logic branch's existence but not its values, and some transmission segment data, as covered earlier. Does a black-boxed component behave identically to the original? It should. The most common cause of a difference is feed-forward signal storage in storage-sensitive custom models. Run both storage settings and compare the results before sealing. Can a black box built in version 5.1 be run in version 4.5? Not by using the compatibility setting alone. That setting affects only the definition script, not the generated Fortran. Older SCAD versions simply lack the version 5.1 master library models the component depends on. What is the C coder for? It translates a PSCAD control module into standalone valid C that compiles outside PSCAD, the bridge from simulation-validated logic to hardware-in-the-loop testing, embedded controllers, and digital twins. How do you check if a component will export to C? Open its definition, go to the script section, drop down the current segment selector, and choose C. If a C script section appears, the component is C coder ready. EMT models are now the currency of interconnection, and PSCAD's V5.1.0 solves two real problems. Black Box compiles a control module into machine code. The original source becomes genuinely unrecoverable, while passive branches stay hidden and the model runs exactly the same. Independent C code does the opposite. It takes validated control logic out of the simulator entirely, compiling to standalone C that runs on real hardware, from HIL rigs to embedded controllers. If your project needs Black Box model review or C coder integration, Keentel Engineering can help. Visit KeentelEngineering.com.